Hello and welcome to basically a bonus discussion around transfer learning. In the last module, there was a discussion around essentially cross-validation and validation and validation of various types of models. It seemed to be tangent to potentially transfer learning, so that's why we're going to talk about transfer learning. That not to mention a no data science, advanced machine learning conversation is complete without some discussion of transfer learning. So we'll work our way through kind of what it is and why we do it and why it's cool and why it's important to understand it. So jumping kind of right in, what is it? It's always a fair question to ask. So what is transfer learning? The basic idea is trying to reuse information and knowledge that was gained in one domain and apply it to a different domain. The idea being that you take something that you have figured out for a particular problem that it ideally does a pretty good job at solving the problem, and then try that approach using it on potentially a different domain, a different set of data. So on the left side of the screen, you see the traditional approach to machine learning. You have something that you want to accomplish. There's some data and a domain that you're considering. You take a model, you train it on that model, and you apply it in that domain. And that's kind of the basic idea of traditional types of machine learning. You might even do something crazy like use AutoML to train your models rapidly using different types of technologies, so different approaches, different types of ways of solving the problem. Transfer learning, on the other hand, is a bit different. So we take the data still that we're interested in for a particular task that we're trying to accomplish, and you potentially take information and a model from some other domain and essentially extract from it the knowledge, so to speak, and then use it to address this other space. So the why would we do it is a good question, and the first answer is, well, it's going to definitely improve performance. You're going to start off at a better place than you would if you're starting off training from nothing. So you basically take a ignorant learner, for lack of a better word, an isolated learner that has no knowledge of the model source, and this baseline will likely improve through the use of transfer knowledge, transfer learning, or knowledge transfer. So hello. I'll go ahead and pause this discussion and check if there are any questions before I get going. So basically what I'm doing here is running through a discussion of transfer learning since Unit 6 kind of talked about it but didn't really. But before I go through that, I'll check any burning questions around your projects or assignments.
Not at the moment, sir.
Okay,
Thank you.
sure. So and I will revisit the earlier modules as we go through. But so basically, transfer learning, the what you see on the left side of the screen is how we typically do traditional machine learning. So we start with some data. That's in a particular domain with a particular type of problem. We train our model on it, then we validate and assess the accuracy of that model, and then we deploy it and use it in basically the same sort of domain in which it was trained. Makes sense, right? That's what we normally do. Transfer learning is a little bit of a different thing. The idea is that you take a model that might have been trained for one problem and apply it to a different one. And you typically have to do a few sort of things to it along the way. But that is kind of part of the game is basically sorry, I wanted to. It's odd. Okay, so that's kind of the point of transfer learning, as always. So why would you do it, right? And there's several different reasons. One, you'll get to something that is good sooner. That's the model development time is going to be considerably faster. You're also going to start off in a better place. So at the point that you go and train something from scratch, you typically start off with a very poor performance. It doesn't do as well to start out of the box, so to speak. So by starting with something that already is doing a pretty good job and basically transferring that information that you've already got around some sort of problem, it'll potentially do it much quicker. So you'll be able to get to an answer sooner than you would if you don't. Also, the overall result is likely going to be better. So no guarantees. That's the nature of things. Is that sometimes there are those exceptions, right? So given that's the case, it's likely to result in a better outcome. So if you consider performance whenever you're considering training with transfer learning and without, you start off with a much steeper slope as you learn, right? So your accuracy is going to improve much sooner and faster. So less epochs, you'll reach a higher level of score. You'll also level out much higher. That's the basic idea here. So whenever you do hit that plateau, you will hit it at a much higher rate than if you just start with blanket training. So there's reasons people do a fair amount of transfer learning. It is a good idea. It's important to understand it, but it's like everything else. It's probably not going to always work, right? So what is it really, right? And so to take it a little bit further, we've got to have some terminology that we've got to get out of the way. So you have this concept of a feature space. The name kind of gives it away. It's the domain in which features exist for the source and target domains, right? So likely, in the case of transfer learning, your domains will be different, although may not. Depends. And also, you may do something like the example that it's talking about here is document classification. So you may be able to apply that to something with you classify documents in English, and then may be able to apply that to a different language, right? So that's the basic idea of taking it from one feature space and moving it to another. The marginal probability is essentially how well it's going to adapt to a different domain, right? So that's kind of the part of it that you want to consider. Label space. This is essentially the place where your labels are coming from, and they're likely going to be different. So if you're wanting to classify something, you're probably going to classify it with a label, or it may be that the label is well, it would be present in your training set as well. And then there's conditional probabilities. Essentially where they're different between the source and target domain. So there's some important questions you have to consider whenever you're doing transfer learning. And it's a relatively complex sort of set of questions. You may start off with, what do you want to transfer? It's the first step in the process. You figure out, what is it that you're trying to, what knowledge are you trying to reuse and gain value from? And also, it's going to be trying to figure out the source specific sort of stuff that you're dealing with. And so figuring out what's different between the source and target, or what is common between them. Then there's also, when do you do the transfer? You when to do the transfer, or if you should. There are scenarios where it might make sense, and there's other times that it might actually make it much worse. And that's the case of this negative transfer. So like everything else, you don't just assume it's going to work out. Just like whenever you're solving any kind of modeling problem, you don't assume that the first model you try is the model, right? You'll try various types of models and see which one does the best for the given domain you're working in. Then the last sort of question is, how do you do that transfer? So there's lots of different ways and approaches that one might use whenever they're deciding how to do it. So there's also different types of transfer learning. There's inductive transfer learning, there's transductive transfer learning, and unsupervised transfer learning. So it's a relatively complex topic. Not going to drain this slide, but it is important to understand that it's a thing, right? It's a thing unto itself. It's bigger than a bread box, so to speak, right? So if we think about um, looking at it from a slightly different place, how does traditional machine learning and relate to various types of transfer learning? And so the this is again, I'm not going to drain the entire slide, but the basic idea is that your source and target domain will be obviously the same as your task. So you're gonna to do it. If you're doing something that's inductive, they're going, and the same thing with unsupervised. The source, target, and tasks are going to be different, but they're going to be similar. If you're doing inductive transfer, it's actually the same source and destination, or source and target domain, and so on. So lots of different things, lots of different ways of addressing it, and it's worth the time, most of the time, to figure it out. And sometimes you may actually um, take a particular um, example where you're taking something from one source into one target, and it fits pretty well. So you might actually do a modification of some sort of approach so that it does something better to improve the performance, such as Ada Boost. So, I must hit the wrong button. When we talk about deep learning, one of the reasons why transfer learning is better is that it potentially narrows the search space, right? So when you're looking for um, a finding a solution to a problem, you may not have to search quite as far because you've already you're starting down the right path initially. Although that being said, there's sometimes it may introduce bias. It may limit too much the search space so that you don't necessarily find the real solution. Also, this is around that whole concept of a generalization, that a model should be able to handle something it hasn't seen before. And it's taking it to the further extreme that it's not just handling something it hasn't seen before, it's doing something different than was originally intended. So how do you really do it? A lot of times you basically take a particular a model and essentially cut off the last couple layers and then put some other sort of classifier or some other piece of the component, a step in the pipeline. And also, you may want to take a look at things like model zoos. So Berkeley has a model zoo that contains a lot of different models. But the basic idea here is that you're by taking off whatever it is it's doing the classification at the very end, you can potentially get better results. So with that, I'll shift over to a demo portion. I'll pause. Any questions so far?
No, sir.
Okay. Give me a moment. Trying to get my
So, are we in the module 6 right now, sir? You said.
yeah, I've ran through pretty much all of the modules. I'll likely circle back and start talking through module 1 and 2 since most people are kind of still there. That's the typical pattern I'll do is kind of run through them pretty quickly at first so that if somebody wants to go quickly, they can. And then revisit the ones, especially if there's something that is slowing people down, so if they're having challenges or something else.
All right. Thank you.
Sure, sure. Any questions you have about the material so far, or something that's
Not at the moment. I'm still in the module 1 and 2.
right?
Way back, way behind. Yes. Just going through that. I'm going through the books and some materials as well.
Okay.
Yes.
Yeah, and if like I said, I'll at some point I'll also probably switch over to more of a an office hours sort of thing where I hang out, and if people have questions, they stop by, right? Um, Where's it at? Zone transfer learning. Let's see if this actually works. So this is coming out of our O'Reilly library, and there's a lot of good stuff inside of there. Let me see if I can get it to come up. And pretty sure this is it. So let's take a look at. Well, actually, I think I'm going to pause this and shift over and talk a little bit more about Unit 1 or Module 1. That may make more sense. Don't think there's much else to talk about transfer learning. No. So, yeah, that probably makes more sense, especially since many are back there. Give me one moment. So the key thing with Module 1 is the deliverable is a paper, right? So you're not going to be writing code. So the point of Module 1 is to kind of introduce the concept of an artificial neural network, right? So this course covers kind of machine learning topics that are that may not have been covered in other courses. And basically, the way I view machine learning is it's applying artificial intelligence techniques at scale to solve problems of some sort, because the purpose of artificial intelligence is to find solutions to problems using various techniques such as statistics or possibly connectionist approaches such as neural networks and so on. And so that's kind of the point. And after Module 1, you should know basically what neurons, nodes, and layers are, and you should know kind of how you use neural networks, the whole concept of training, how the error and adjustments are done through the backpropagation process, and what a gradient descent is. So the foundation for neural networks, as the name kind of implies, was our understanding of neurons in the brain at the time that it kind of came to be, which was back in the 50s, right? So obviously we've made some advances in our understanding of the brain somewhat, but there's still, it's an unknown problem because it is a complex thing. So the basic idea is to take the concept of how the pieces we know of a neuron and how we think they work and try to apply it in a similar sort of approach. And basically it kind of comes down to you've got some inputs coming in. So for a particular neuron, you've got basically one input, and then you've got some weights and some biases that are going to be applied. And then you have a function that you consider of when you produce output, or if you produce output, how much output do you produce. So it's essentially deciding when something turns on. And so another way of looking at that same sort of thing, we take a collection of these neurons, these artificial neurons, and put them into layers and turn those into basically things that are connected to each other, typically fully connected, right? So you have an input layer, you have a hidden layer that's basically just between the input and the output, and then you have output. If you have a deep neural network, you got more than one hidden layer, right? So there's n numbers of layers between the input and output, not just one. At the end of it all, it comes down to basically this concept of taking your inputs, multiplying them by the weights, adding them up, and then deciding if it's time to do something or not. And sometimes you need to move around the values to decide when you do something or not, and that's where we use essentially a bias to kind of shift things around. So you can think of it very much as a function that is the summation of the weights times the input. So the visual representation of a fully connected three-layer neural network, this is kind of the hello world of neural networks, right? So you've got 3 inputs, 2 outputs, and 4 in the middle. The structure of these things is not necessarily a science. Sometimes it's about experimentation and figuring out how many layers you need, how many nodes you need in each layer, and so on. Although typically your input and output are going to be related to the operation you're trying to perform. So if you're doing binary classification, you might very well have output that are 2, right? So yes or no. And if you're doing something that is classifying larger number of sets, then you're probably going to have more outputs. Your inputs are going to be related typically to the features that you have going in, and so on. So that's kind of the basic sort of rule of thumb. Again, the whole concept of a weight and bias is that you take a particular the summation of the weights times the inputs plus the bias, and then we'll compare that to an activation function, or apply an activation function to it. There's several different types of learning. This course is mostly focused on supervised learning. The idea is that you know the answer, right? So there's a labeled data set, and you know what it is you're looking for. And you're typically trying to essentially fit something to basically a curve of some sort. Taking it into higher dimensions, you're fitting a plane to a series of points and so on. And up to higher levels where you have a hyperplane that's going into n-dimensional space. But it's basically around trying to approximate a solution through an informed sort of way. Again, no guarantees that you'll find the optimal solution, but you typically find one that's good enough, and good enough often means not necessarily the highest accuracy, but the highest accuracy with the highest general ability or generalization ability. So the idea is that you can take a neural network that has been trained with a certain amount of data, give it data it has never seen before, and it should do pretty well. If you're never going to see new data, then there's probably better solutions, right? So if you're only going to be classifying or doing whatever operation against a finite set of data, you might find yourself doing better with something like a decision tree or some other approach. If you're going to see stuff that you've never seen before, that's when you start thinking about things like neural networks. Unsupervised learning is typically around kind of things like clustering. You're basically looking at patterns and so on. You don't know the answers necessarily, but you kind of are looking for something out of it. You generally only do that if you don't have a choice about it. You may not be able to actually get a labeled data set. Also, labeling data sets is hard. It takes time, takes money, takes a lot of effort. So that's part of why the supervised approaches are very challenging. Not mentioned here, but is relevant, is reinforcement learning. It's similar in a way to supervised learning, except you don't necessarily have labels, and you don't necessarily know what something is. But what you do know is what good looks like, right? So you have a function similar to what we do in genetic algorithms. You have a function that helps you determine if you're getting better or not. And so the basic approach, again, kind of similar to genetic algorithms, is to balance between exploring the search space, and that's done oftentimes through random sort of random selection of characteristics. It's between that and optimizing to use the knowledge that you have and get the best outcomes you had based upon what you already know. So it's kind of the mixture between exploitation and exploration of a search space. But in this course, we're focusing mostly on supervised learning. The term epoch basically means that it is a single iteration all the way through your input, and you've updated all your weights and propagated back any kind of errors. And so it's taking all of your data, running it through one time. Generally speaking, there are a lot of epochs when you're doing your training. And you will typically at each epoch consider how well you're doing as far as both the kind of the loss and the accuracy, and decide if you want to keep going or not, right? So, and also you oftentimes will checkpoint at an epoch, so you'll save off the weights essentially for your neural network in case something happens, like your computer goes off, right? So that allows you to be potentially resume where you were at in the training process. An activation function we've talked a little bit about. It's basically a way of converting from input to output. It's lots of different types of them. At the end of it all, it's a function, literally, as the name implies. Mathematical function that takes some inputs, typically a input, and returns an output. And sometimes that output is binary in nature, so you may have something that literally goes from 0 to 1, and you may have something that does something in between, a continuous function, if you will, of some sort. And it allows you to do various approximations of similar things. Feed-forward networks, things kind of just go forward, right? So talking about activation functions, this is a step function and a sigmoid function. As you can see, the step function goes from 0 to 1 at the point that the activation threshold is reached, right? So at the point that you reach the threshold, it turns on. Sigmoid is going to be more of a continuous thing, and so you can essentially adjust the bias to move around that threshold. That's kind of what we're doing, is it allows you to control kind of where it is. Ways that you can implement these logical functions using sort of a very simple sort of construct, the McCulloch-Pitts unit. And so you can see and, or, and not. Also, a more simple sort of example of a feed forward. We have some values coming in, we have some weights that are being applied, and then we're producing a result with some sort of an activation function going in there. So when we look about, no conversation about neural networks is complete without a little bit of a discussion of a perceptron. It was an early algorithm, still in use. They're still being used, and it basically allows the units to operate separately without having shared weights. So each weight is per item. And so you basically, it allows things to move around the shape of the space. It can do some pretty good stuff with a perceptron, but it can't handle exclusive OR, which is kind of a little bit of a problematic thing because it can't kind of divide between the two things. Computational graphs, went over this before. It's a fairly complex thing, right? A graph, first of all, is a collection of nodes and edges, or vertices and arcs, or pick your term, but it's basically something that is connected to something else. We can convert operations, mathematical operations, into a graph, and we often do. And the basic idea is to make it such that you can kind of understand what's going on, and more importantly, it's oftentimes to control what processing actually occurs. An example of a graph is parsing the mathematical formula into the components, and then setting essentially some values into them, so you can essentially get back a result in an intelligent way. Similar sort of concept occurs whenever you're dealing with some big data technology such as Spark. They actually utilize a similar sort of construct to represent the operations within a job. So It is a way of describing lots of things, including deep learning models. It is it's can be fairly complex, and that's why we'll just kind of skim over it pretty quickly. Again, mathematical graph. The edge is the line between the nodes. In this case, that represents the functional argument, right? So it's the argument that's going through. It's not just pointers, but there's a value associated with it, and they have direction. So obviously the source to destination lets you know kind of how it's going to work. A representation of a feed, a forward propagation sort of network. Convolutional neural networks, you talk about that quite a bit in this course as well. And the key things that they do is apply this concept of a kernel, which is a pattern of weights that are being applied across multiple local regions. So you take a kernel function essentially and apply it to a portion of what it is you're looking across. And that process of applying it is called a convolution. And then you have the should be first unit in the first hidden layer. So you have a receptive field, a pool, and then a tensor and a GPU. So tensors are essentially a way of doing multi-dimensional processing. So that's where the name TensorFlow is coming from. So it allows you to do at the end of the day, this stuff turns out to mostly be matrix multiplication, right? So you're multiplying things together. Your inputs and your weights turn out to be basically matrices that you're multiplying together. And so the key concept with a convolutional neural network compared to a traditional kind of hidden, a typical hidden layer deep neural network is around kind of this concept of looking at things in multiple dimensions. So it allows you to consider the proximity of one thing to another thing, not just necessarily taking it and flattening it out to a long array of bits. So it works out well for things like image processing. Recurrent neural networks is essentially something that has a cycle in the graph. So they often have a form of memory associated with them as well. And there's this concept of a long short-term memory, which is essentially a certain amount of memory that's being copied from time step to time step, typically with either some sort of fading or gating to make it sort of remove things from memory so you don't get locked into a certain state. Whenever we talk about neural networks, we talk about their structure. There's the typical ones that are just feed forward, and those are going to be essentially perceptrons with multiple or single layers. Also, they're stateless versus a recurrent neural network is essentially going to have a certain amount of memory associated with it as well. The computational graph for it, and that's basically just showing that there is iteration within a particular a neuron. So, and a computational graph from a recurrent neural network as well. Applications, we use neural networks in lots of stuff: vision, natural language processing. So if you're talking to your smart devices, under the covers, there's some neural networks being used. Same thing if something is scanning your paper and doing OCR, right? That's likely going to be utilizing some neural networks. Reinforcement learning, it's how IBM and DeepMind beat a Go champion, which is Go has considerably more states than things like chess, so no small accomplishment. So that's some of the concepts of where they're being used. I'll skip over that. Talk briefly about the deliverable. So you're asked to explain what an artificial neural network is, right? So, and as always, we'll be using a rubric. That's how I grade. That's how I have to grade. And so you're basically working at a robot company. So you've been tasked to develop a paper on the various components of artificial neural networks used by the company's robots. You need to explain how artificial neural networks function and provide an example, provide a definition of neurons, nodes, layers, and explain how they are interrelated. How many, how that neurons and nodes are similar in nature, and that we put them into layers and connect those layers together. Define and provide an example of the backpropagation process, and also what gradient descent is, and why we use it in machine learning. And then basically turn in your paper with in-depth coverage of these topics in a Word document. The rubric corresponds to those three things you were asked to do. So it talks about that you've explained how artificial neural networks function. Then you talk about what neurons, nodes, and layers are and how they are related. And then you talk a bit about backpropagation and gradient descent. So those are the high-level points. And so with that, I'll go ahead and wrap this up. So I'll pause for questions if you have any.
So the deliverable 2 is also a paper, right?
Yes, I believe so.
So first, okay.
Yeah, yep. All right. Well, for those of you watching the recording, thanks for watching. And as always, it's nice to have somebody in the room, so thanks for stopping by. And we'll talk again next week. So if you have any questions, let me know. That's what I'm here for.
Thank you, sir.
Sure thing. All right. Have a good day.